Building a structure that will outlast its makers starts with a single, uncompromising flat line. Before the first blocks touch the ground, the concrete foundation is drilled to receive its load. A crane delivers pallets of aerated concrete directly to the slab, minimizing the distance materials have to travel by hand. But raw concrete is porous, acting like a rigid sponge against ground moisture. The builders begin by rolling out a thick black damp-proof membrane along the perimeter. This thermal and moisture break is critical. Capillary action would otherwise pull water straight up into the masonry. The first course of masonry dictates the geometry for the entire structure. If the base layer is out of level by a fraction of a degree, that error multiplies exponentially as the walls rise. Mortar is laid directly over the membrane, acting as a leveling bed to compensate for slight imperfections in the concrete slab below. White aerated concrete blocks are highly favored for their exceptional thermal resistance and lightweight profile. Composed of quartz sand, calcined gypsum, and lime, they contain millions of microscopic air pockets. This cellular structure provides insulation without sacrificing compressive strength. Each block is coaxed into perfect horizontal alignment with a rubber mallet. A spirit level verifies the work on all axes, ensuring the foundation is absolutely true before the mortar begins its chemical cure. With the initial bed established, the structural corners anchor the next phase of the build. Corners are the geometric reference points of any masonry structure. They must be perfectly plumbed to prevent the entire wall system from shifting out of square. The craftsman relies on a rubber mallet's deadened impact to adjust the massive blocks, striking two hard risks, fracturing the aerated concrete. The wall begins its steady climb, course by interlocking course. As the perimeter walls reach waist height, the focus shifts to maintaining an unbroken horizontal plane. Aerated concrete requires specialized thin-set adhesive mortar rather than traditional thick cement joints. A metal trowel is used to spread a slurry coat across the top surface, sealing the pores of the blocks. This pre-wetting or sealing step prevents the dry concrete from rapidly absorbing the moisture out of the next adhesive layer. If the adhesive dries out before curing, it loses its structural bond. It is a constant race against evaporation. The thin-set adhesive is applied with a notched trowel, creating a ribbed pattern of uniform ridges. These ridges serve a specific mechanical purpose. When the next block is set, the ridges collapse evenly, pushing out trapped air and creating a full coverage, void-free bond line measuring just millimeters thick. The tight joint minimizes thermal bridging, keeping the wall's insulation properties intact. Once seated, the block is tapped down to interlock with the mortar bed. Continuous spirit level checks ensure that no block rides high on an excess ridge of adhesive. Masonry walls have enormous compressive strength, carrying vertical loads with ease. But they are inherently weak against lateral or bending forces. To introduce tensile strength, a continuous channel is manually scored into the top of the blocks. Every particle of dust must be swept clear, as loose debris acts like a dry lubricant that prevents mortar from gripping the steel. A solid steel reinforcement bar is dropped directly into the groove, locking the perimeter together. One of the primary advantages of aerated concrete is its extreme workability. Unlike dense cinder blocks that require diamond blades, this material can be cut to precise dimensions using a specialized hand saw with carbide-tipped teeth. Custom cuts allow the wall to maintain a staggered running bond pattern. This interlocking geometry distributes stress evenly down through the foundation. Moving to the exterior, managing groundwater becomes the next critical priority. Even the best foundation will eventually succumb to hydrostatic pressure if water pools against it. An excavator carves a deep perimeter trench, dropping below the frost line. The base is lined with a tough, permeable geotextile fabric. This synthetic membrane acts as a soil filter. It allows water to pass through freely while preventing fine silt and clay from washing in and clogging the drainage system over time. A perforated orange drainage pipe is pitched at a precise downward angle toward a collection ring. This network creates an artificial path of least resistance, intercepting groundwater before it ever touches the structure. The excavator backfills the trench, burying the defense system. Out of sight, it will quietly protect the masonry for decades. High above the foundation, structural integration continues. Heavy wooden beams, reinforced internally with steel, are hoisted across the load-bearing spans. These headers bridge the open gaps in the architecture, transferring the weight of the future roof out to the solid masonry columns. On the ground, the transition back to wet concrete begins as the mixer churns a fresh structural batch. Creating a monolithic concrete bond beam along the top of the wall ties the entire building envelope together as a single rigid unit. Wet concrete is manually passed up and poured into the wooden formwork, completely enveloping the heavy steel rebar cage suspended inside. But pouring is only half the structural equation. Obvious. A mechanical concrete vibrator is plunged deep into the wet mix, sending high-frequency shockwaves through the heavy slurry. This intense vibration is absolutely critical for the beam's integrity. It temporarily liquefies the stiff concrete mixture, breaking the surface tension and forcing trapped air bubbles to violently rise to the surface. Without this consolidation, hidden honeycombing and air voids would form around the steel reinforcement, leaving critical weak points in the load-bearing header. Once the air is expelled and the heavy aggregate settles completely, the top surface is struck off and smoothed perfectly flat, capping off the masonry walls. The final courses of aerated blocks are laid into their mortar bed, bringing the perimeter walls to their peak height. Constant checks with the long spirit level verify that the structure hasn't deviated a millimeter during its vertical climb. With the masonry topped out, the focus shifts to creating a continuous reinforced cap. The crew secures heavy wooden formwork directly to the uppermost blocks using power drills. These planks will act as the rigid, temporary mold for the final concrete tie columns. Vertical steel rebar rods protrude upward from the cores, waiting to be permanently encased. The wooden forms must be securely fastened and heavily braced to withstand the immense hydraulic blowout pressure exerted by the weight of the wet concrete. If a form warps or bursts during the pour, the structural geometry is instantly ruined. On the ground, preparations begin for the primary slab. A trench is manually excavated along a taut yellow string line, establishing the exact outer boundary for the concrete edge. A long screed board is used to shave down high spots in the soil. A flat, uniform subgrade ensures the future concrystant thickness without structural thin points. In Fompens, The loose soil and gravel base must be heavily compacted. A mechanical plate compactor violently forces the aggregate to interlock, driving out air and preventing future settlement that could crack the floor slab. The gravel is sprayed down to prevent the dry earth from instantly wicking the moisture out of the wet concrete later. Inside the upper formwork, heavy threaded steel rods are wired directly into the rebar cage. These bolts will eventually anchor the wooden roof, trusses securely to the concrete frame, tying the timber roof to the heavy masonry walls to resist high wind loads. A monolithic floor slab acts as the foundational diaphragm, tying the independent walls together at the base. The crew rolls out a continuous heavy-gauge plastic vapor barrier over the compacted gravel. This sheet permanently stops subterranean moisture from migrating up through the porous concrete. Over the plastic, a rigid steel mesh grid is laid out, providing the critical tensile strength needed to prevent the expansive slab from cracking under thermal expansion and heavy live loads. The mixer truck chute releases the final payload, flooding the grid with thousands of pounds of wet concrete. The crew works swiftly to rake and screed the heavy material before the hydration process makes it unworkable. Hand floats and long-handled magnesium screeds are pushed across the wet surfaces, pushing down the large aggregate rocks and drawing the fine cement paste up to the surface. This careful finishing leaves a dense, glass-smooth layer that cures into a highly durable floor. What started as an empty patch of earth is now a hardened, permanent geometry. Every hidden layer of gravel, steel, and block now operates as a single, immovable system. The foundation is complete, ready to bear the weight of whatever comes next.